Today we're going to be looking at section 5.3, combining functions. I'm more formally known to me as composition of functions. Our four objectives are to combine functions arithmetically. We're going to compose functions, decompose functions, and we're going to use functions to solve applications. So combining functions arithmetically. Here are our four objectives. You see that when you see a plus between the two, we're going to be adding two different functions. Subtraction sign, you're going to subtract them. No sign, they're just butted up against each other. You're going to multiply them together. And then, of course, a fraction, you're going to divide them. And this says provided that the bottom is not 0. You always got to be aware that when you have a fraction that you cannot divide by 0. So these are just the terminologies or symbols that let you know what to do with the functions. Here's some examples provided. I think these are really good to kind of show you what's going on. And then they also start plugging in numbers, which we'll do some of that in the examples that I will show you here shortly. So another example. And then here's some graphic examples, and they talk about how the domain of f and g, when you combine them. I don't think I saw that note yet, but let me continue, and it may show it. No, I didn't. Okay, so let's talk about the domain, because I did not see it expressed. Maybe I just overlooked it. The domain is the intersection of those functions. So let me go all the way back. Normally they have it, unless I just really overlooked it. Yeah, here we go. Domains of f and g individually when added. Condition. Sorry. The domains of f and g are going to be the individual domains where they intersect. So that's going to be for 1, 2, and 3. So when you add them, subtract them, and multiply them, the domain will be what you get if you were to intersect them or overlap them with each other where they intersect. The only difference is when you do f divided by g, you have to remove the condition that makes the bottom 0. So you would start with the intersection where they overlap, and then you would get rid of whatever causes the bottom to be 0. So that's what this is saying. Domain of these functions consists of elements or the intersection of the elements. Okay, so they did kind of point it out. I just kind of went past it. So as you go through and look at these examples, this is kind of what they're saying here. The domain of this parabola is all real. The domain of the other parabola is also all real. So your domain would be negative to positive infinity. However, whenever they do division, whatever the g function is, the bottom can't be 0, so they would remove 1 point, and then that's kind of what they're explaining here. So all real numbers, and then g cannot be 0, so whatever makes that bottom 0, which I think is 2 on that blue graph. Blue is f, red is g, so you got 2 points where it's 0, negative 2 and positive 2, so you have to remove both those points, and then you get 2 breaks in your line, so you got 3 different sections. Which I'll show you that a little bit more formally in the examples that we do. Then we go to composition of functions. This is the symbol. It looks like a little degree symbol between f and g. It does not mean multiplication. A lot of people think that. And then here is another way of rewriting it. So f composed of g, or f of g, can be written like that, is what you get when you take your f equation and then you plug in the g equation everywhere you have an x in the f equation. And I know that's a mouthful and can be a little bit confusing, but as you see it, it'll make more sense. And again, it's telling you it's read as f of g. So this domain works a little bit differently. So the domain of f composed of g are all the x's in the domain of g, because that's what we plugged in for f, that work for f. And then I'll show you that as we work through that. And so here's just an example or a little image to kind of show you what's going on. Then here's some examples that they're going through and showing you some graphs. I think all this is really good to kind of read through and follow through. And then some more examples provided and talking about the domains of compositions of functions. And then some more domains. So I guess one thing I will point out is that when you're doing the domain, you will have restrictions in some cases when you have square roots or fractions. And whenever you plug in, you got to remember to account for those restrictions. But again, like this one specifically, you'll have your domain, you cannot be greater than 4, but we'll show you a little bit more as we start doing it, because you'll have restrictions here under the square root, you can't have negative, and you also have restrictions here, you can't be 0. And depending on which one you plug in, will cause you to focus on one set of restrictions and not the other. So for example, let me see. Do they do F composed of G, F composed of G? So in G, you can't use a -1. That would cause this to be 0. However, when you take and plug it in here, with this domain, you couldn't use anything less than 5. That will change. So you have to, whenever you plug in, -1 would come with this, because you couldn't use a -1 here. You can't use it when you move it over here. And then the domain restriction here that was anything less than 5 would now change according to when you simplify. But again, I will show you that as we begin to work it out in the homework section. And then decomposing functions, so you go forward and backwards. The best way I would like to explain this is that you have an inner function and an outer function. So they will give you something called h of x, which is like a final function. And I would think about this as an inner function and an outer function. So the cube root is the outer function, whatever the grouping symbol is. So everything inside I would use as the second equation that got plugged in. So I would use that as like the g of x. And then the outer function, I would use that as the f of x and just replace everything down there with an x. That is the simplest way to do it. So that's what they're doing here. They're saying that g of x is equal to the cube root of x, which is probably backwards from what I would do it. And then they say h of x is equal to this, and they work backwards to find what they are. There's multiple ways to do them. There's not one correct way, but the more you practice with it, you'll see that. Here's some examples that they provide, and here they're telling you that there are not these are not the only possible solutions. So there's like an infinite number of ways you can probably write composition of functions, and we'll show you a few as we practice. And then the last one is just kind of like a little neat mathematical graphic. We won't be doing this, but it's kind of talking about the mathematics behind plugging a function into itself over and over and over again. And you get these neat little patterns. Looks like a chaotic pattern, but it's really neat with the computer program showing you what's going on. And this is just kind of explaining a little bit behind how that was developed. A lot of math is just, somebody was wondering, hey, I wonder what happens if you do this, and what would it look like, and just playing with it and trying different things out. And then later on, applications came. So it's kind of neat, just kind of looking at that and reading over where it came from. All right, with that, we're going to stop, and we're going to go ahead and start the homework examples.